This is a continuation of the lecture on Newton's law of universal gravitation and satellites. I do want to talk about the inverse square law, which just means a law where you have something that's related to 1 over r squared. We're going to be seeing an inverse square relationship in many different physics relationships in the next few months, and this is the first one we've seen. One thing to think about is the notion of a sphere. And spherical surface area is 4 pi r squared. So if you have a mass in a spherical shape and it has some source strength, and in this case we're talking about gravitational strength. We'll also talk about light radiation strength. We'll be talking about electric strength. We're going to be talking about magnetic strength. There's other inverse square laws. But for now we're talking about gravity. The idea is that if you want to understand what's going on the surface of the Earth, you talk about setting up a relationship between the strength divided by the area of that little surface. And it turns out that gravity, g, the gravity that we know, 9.8 meters per second squared, is, if we say that g is the gravitational value on the surface of the Earth, and then we think, well, what happens to this gravitational value as you get further and further away? So here's the gravitational value when you're on the surface of the Earth, but as you get further and further away, as the radius gets larger, as you go from the radius of the Earth to twice the radius of the Earth, then you figure out that that little chunk of area through which the strength might be projected, see it's coming through here, the area has just increased by 4-fold. And because the area has increased, then the overall strength in one little section of area has decreased by 1/4, and so forth. So if you go out 3 times the radius, then that little surface area chunk that's relative to the initial strength coming through is now going to be 1/9 what it was. And so what you realize is that the gravitational strength drops off by a function of 1 over the radius squared. Anyway, so it's an interesting relationship when you think about the surface area sphere and how as you get further and further away from the center of a sphere, that surface area gets larger, which diminishes the effect of this strength of a gravitational pull or other types of forces we'll talk about later. Okay, but how can you use that? As satellites orbit the Earth, what keeps them in circular or nearly circular motion? In most of the problems we're going to talk about, we're going to assume uniform circular motion. So, knowing Newton's law of universal gravitation, what is the tangential speed of a satellite? So if you think about the Earth, okay, so here's the Earth, which has a mass of the Earth, and then you think about a satellite, okay, I'll put a little m of a satellite. If the Earth were just sitting right here, and the satellite were sitting right here, and the satellite was not moving, then the satellite would feel a force of attraction towards the Earth. Actually, the Earth would feel one towards the satellite as well, but it's so massive it wouldn't move very much. But the satellite is going to feel a force of attraction towards the Earth. What force would it feel? Well, it's going to feel the force of g times the mass of the Earth times the mass of the satellite divided by the radius squared between them, the radius being from here to here. Okay, so if you just held the satellite up above the Earth and you let it go, it's going to feel a gravitational force. Now, the force that satellite feels when it's really far away from the Earth is going to be pretty small compared to what we feel here on the surface, but nevertheless, it's enough to pull that satellite towards the Earth. Now, if you take that satellite and you put it in motion, so let's get this going in motion. Let's say you get it going in this direction, then that force that's going to pull the satellite, instead of pulling it towards the Earth to collapse and crash into the Earth, it's just going to hold it into an orbit if you get it going just the right speed. So I'm going to go ahead and blank this out and start and just talk about how if you have the mass of the Earth here, here's your Earth, and you have your satellite and it's moving around in a rotation around the Earth, it's only doing that because it feels a centripetal force, and the force it's feeling is gravity. And that satellite is actually in free fall, in the sense that it's falling towards the Earth, but it's going so fast that it just remains in orbit around the Earth. It never actually falls in and spirals in and crashes the Earth. It's going at just the right speed. Well, what speed is that? If the force of gravity, we know that is going to be gm times the m of the satellite, mass of the Earth, over r squared. That's the force. That's got to be what's holding that thing in orbit, which is going to be equal to the mass times the acceleration of the satellite. And so that's the mass of the satellite times the acceleration of the satellite. Okay, so, I'll cut our erase again. Let's get this out of the way. So, mass times acceleration of a satellite is the same, if it's in circular motion, it's just mv squared over r. So if you want to know what v is, you say that m of the satellite times v squared over r, and r is the radius from the satellite to the center of the Earth, okay, is equal to g times the mass of the Earth times the mass of the Sun over r squared. That's the force that's pulling it. That's the gravitational attraction. And this represents the centripetal force, and that's mv squared over r if you know that tangential speed. So now you'll see that the mass of the satellite cancels from both sides, and you can bring one of the r's over here, okay, multiplying both sides by r, and that'll go away, and you'll lose one of those. And so we'll get v squared is equal to g times the mass of the Earth, I just ran out of space, times r. Okay? So, to find the speed, then you just take the square root of that. Anyway, it's the relationship between this force, this gravitational force that's pulling the satellite in, and the centripetal movement, this mv squared over r, that allows you to find the tangential speed of your satellite. Geosynchronous orbit is an interesting case where you have a satellite at a very specific altitude. And so here's your radius from here to here. That's your very specific altitude. In this case, it was 22,284 miles. If it happens to be at that height, it'll be traveling at 6,872 miles an hour. And that speed, along with that altitude, makes it so that it'll go all the way around one orbit in exactly 24 hours. How is that helpful? If it makes one complete rotation of the Earth in 24 hours. Well, if the Earth makes one complete rotation in 24 hours, and the satellite makes one complete rotation in 24 hours, that means that the satellite is going to be located directly over one point in space. And so you can hold, if you get your satellite moving, you can hold that location and it will rotate right with a particular location on the surface of the Earth. So we say it's geosynchronous because the satellite is synchronized with the rotation of the Earth, and it can hold its location right over one spot of the Earth. And that concludes our discussion.